Welcome to this explainer. Today, we're diving right into an incredibly fascinating, microscopic drama that literally dictates so much of the macroscopic world around us. We're stepping into the realm of organic chemistry to meet a very special family of molecules. We call them the carbonyls, and specifically, we're going to look at them as two contrasting sibling molecules, aldehydes and ketones. Now, even though they share a fundamental family resemblance, their personalities, their behaviors, and their ultimate destinies absolutely could not be more different. I'm really excited to guide you through their life cycle today.
Okay, let's look at our roadmap. We'll trace the entire life cycle of these molecules across 6 sections. First, we'll meet the carbonyl family. Then, how to build carbonyls. After that, physical traits and quirks, followed by chemical reactions and behavior. Next, we'll look at testing and identifying carbonyls, and finally, the real-world uses of carbonyls.
Section 1. Meet the carbonyl family.
So both of these siblings share a core trait, and that's the carbonyl group. It's simply a carbon atom double bonded to an oxygen atom. That specific bond is the absolute beating heart of their chemical identity. But to really understand these siblings, we have to look at their different personalities, which are completely based on where that carbonyl group actually lives. I like to think of aldehydes as the outgoing siblings. Their carbonyl group lives right on the edge, the terminal end of the carbon chain. Because they're exposed like that, they are highly reactive. When naming them, chemists use the suffix -al, like in methanol. Ketones, on the other hand, well, they're the stubborn protective siblings. Their carbonyl group is tucked safely right in the middle of 2 alkyl groups. They use the suffix -one, like propanone. And that positional difference, it changes absolutely everything about how they behave.
Which brings us to a very important number, 120 degrees. The carbonyl carbon is sp2 hybridized, which is just a fancy way of saying the molecule arranges itself in a flat, trigonal planar geometry with bond angles of exactly 120 degrees. But what's absolutely crucial here is the magnetic tug-of-war happening within that bond. You see, oxygen is highly electronegative. It's basically an electron hog. It pulls the shared electrons towards itself, creating a slightly negative charge on the oxygen and a slightly positive charge on the carbon. This intense polarity is the driving force behind almost all of their behavior.
Section 2. How to build carbonyls.
So how do we actually bring these specific molecules into existence? Let's open up the chemist's cookbook and look at the preparation phase. One of the absolute coolest ways to build a carbonyl is through a process called ozonolysis. Just imagine taking an alkene, so a molecule with a carbon-carbon double bond, and blasting it with ozone. The ozone attacks that double bond and creates this unstable temporary structure called an ozonide. Then by adding some zinc dust and water, you cleave or just chop that molecule right down the middle. The result? You've successfully birthed new aldehyde or ketone molecules, along with some hydrogen peroxide, all depending on the exact shape of your starting alkene.
Now, what's really interesting here is how another method, the hydroboration oxidation of alkynes, shows us that starting position is pretty much destiny. If you start with a terminal alkyne, meaning the triple bond is hanging out at the very end of the chain, you will always yield an aldehyde. But if you start with a non-terminal alkyne, where that triple bond is buried safely inside the chain, you're going to yield a ketone. The architecture of the parent molecule completely dictates which sibling gets born.
Section 3. Physical traits and quirks. Let's shift gears and translate these invisible microscopic structures into macro-scale sensory experiences. Things you can actually see, boil, and even smell in a lab. Let me pose a quick question to you. If you drop these molecules into water, they'll dissolve beautifully, but only up to a certain size. Once they get too big, they stubbornly separate. Why do you think these molecules dissolve in water, but only up to a point?
Well, the answer lies in a tiny battle between the polar head and the nonpolar tail. Up to about 4 carbons long, aldehydes and ketones are perfectly soluble in water. And that's because their polar carbonyl oxygen can form nice hydrogen bonds with the water molecules. But as you add more and more carbons, those bulky, hydrophobic, literally water-fearing, alkyl chains start getting in the way. They physically block that hydrogen bonding from happening. So the larger the molecule gets, the more insoluble it becomes in water. Though interestingly, they will still happily dissolve in organic solvents like benzene and ether.
Section 4. Chemical reactions and behavior. Now that we have our carbonyls sitting in a flask, what happens when we introduce them to other chemicals? The defining reaction for this whole family is called nucleophilic addition. Remember that electron tug-of-war we talked about earlier? Because oxygen hogs the electrons, the carbon is left with a slight positive charge. That makes it act like a giant bullseye for nucleophiles, which are simply electron-rich attackers. And here is where the sibling rivalry really peaks. Aldehydes are highly reactive to this attack because they're totally exposed at the edge of the molecule. Ketones, however, are surrounded by bulky alkyl groups that physically block the attacker, making them much more stubborn and way less reactive.
And this brilliantly illustrates the sheer elegance of organic chemistry. When carbonyls undergo nucleophilic addition with ammonia derivatives, they follow this beautiful, predictable pattern. The reaction kicks out a molecule of water, and the names of the products line up perfectly. Check it out. Hydroxylamine yields an oxime, hydrazine yields a hydrazone, phenylhydrazine yields a phenylhydrazone, and semicarboxide yields a semicarboxone. Once you see that underlying structure, you don't have to memorize 100 different reactions, you just follow this really beautiful, predictable logic.
Section 5. Testing and identifying carbonyls.
Imagine you're a chemist with an unmarked flask. You know it's a carbonyl, for sure, but you don't know if it's an aldehyde or a ketone. How do you interrogate it? Well, one of the most visually stunning ways to do this is with Tollens reagent, which is just an ammoniacal silver nitrate solution. Because aldehydes are the outgoing, easily oxidized siblings, they will react with this weak oxidizer, reducing the silver ions to solid metallic silver. This creates a highly tangible, literal silver mirror coating the inside of your test tube. It's amazing. Ketones, being incredibly stubborn, won't react at all. They need drastic conditions, like boiling in nitric acid, just to break their bonds. So if your tube turns silver, you know you definitely have an aldehyde.
Another great interrogation tactic is the iodoform test. Here, you add sodium hydroxide and iodine to your compound, and what you're looking for is the sudden formation of a precipitate. If the molecule happens to be a methyl ketone, meaning there's a methyl group sitting right next to the carbonyl, it will react to form this bright yellow, terrible-smelling solid called iodoform. It is a wildly vivid, unmistakable chemical tell.
Section 6. Real-world uses of carbonyls.
So we've seen how they're born, how they act, and how to test for them. Now let's look at how these chemical traits actually translate into real-world applications that impact your daily life. The crucial point here is understanding the sheer scale of their utility. Take this number, for example, 40%. A 40% aqueous solution of formaldehyde, which is the simplest possible aldehyde, is famously known as formalin. If you've ever seen biological specimens preserved in a museum jar, you were looking right at formalin at work. The reactivity of that tiny molecule makes it an incredibly powerful preservative.
But the careers of the carbonyl siblings vary wildly. While simple formaldehyde is used to preserve specimens or create incredibly sturdy plastics like bakelite, the larger, more complex siblings take on a totally different role. Benzaldehyde is heavily used in the perfumery and dye industries. Molecules like butyraldehyde and vanillin provide distinct, really pleasant flavors and odors. Then you have things like ethanol, which is a starting material for acetic acid and various drugs. And of course, overall, they are widely used as vital industrial solvents. Their distinct chemical personalities map perfectly onto a vast array of industrial functions.
We have traced the life cycle of aldehydes and ketones, from their sp2 hybridized birth all the way to their varied careers. And it leaves us with a truly mind-bending thought to wrap up this explainer. Just think about it. If a single oxygen atom's tiny, invisible magnetic tug-of-war can create everything from a bad-smelling yellow solid in a test tube to the sweet, comforting scent of vanilla in your kitchen, what other invisible molecular dramas are constantly shaping the vast, macroscopic world around you? Thank you so much for exploring this with me today. Keep wondering, keep learning, and I'll catch you next time.